The concept of non-locality has challenged traditional interpretations of physics for decades, particularly in the realm of quantum mechanics. In classical physics, interactions are thought to occur through local observable forces. Objects can only influence one another when they are in direct contact, or when a force is exerted through a local field. This local cause and effect understanding is intuitive and aligns with our everyday experiences. For example, Newton's laws of motion explain how forces interact with objects in a sequential, observable manner, allowing us to predict outcomes based on initial conditions. However, in the quantum realm, non-local phenomena such as quantum entanglement defy this traditional understanding. Entangled particles demonstrate that two objects can become so interconnected that their properties are correlated, no matter how far apart they are. Changes in the state of one particle can instantaneously affect the other, a phenomenon that has been experimentally verified, yet remains difficult to explain within the framework of classical physics. This non-local interaction does not fit into the classical view of forces acting over distances or through fields in a step-by-step causal sequence. Quantum mechanics attempts to deal with this through the concept of wave functions. When particles become entangled, their wave functions are said to merge into a single system. This merged wave function provides a mathematical description of the system as a whole, treating the entangled particles as if they are one entity rather than two separate objects. While this approach has successfully predicted experimental outcomes, it is largely reductionist. It focuses on the mathematical probabilities of outcomes rather than offering a mechanistic explanation for how non-locality occurs. Einstein, Podolsky, and Rosen, EPR, famously criticized this lack of explanation in their 1935 paper, where they referred to quantum entanglement as spooky action at a distance. Einstein, in particular, resisted the notion that information could travel faster than the speed of light, as non-locality seemed to suggest. He believed that there must be hidden variables, some underlying mechanism that could restore a classical local understanding of reality. However, Bell's theorem and subsequent experiments showed that no local hidden variables could explain the correlations seen in entangled particles. The reality of non-locality was confirmed, yet a logical causal mechanism remained elusive. This is where current interpretations of non-locality fall short. While wave functions and quantum probabilities provide a mathematical tool for predicting the behavior of entangled systems, they offer no logical structure to explain how these systems are interconnected. Quantum mechanics tells us what happens, but not why it happens in this non-local, instantaneous manner. As a result, non-locality remains a mathematical abstraction rather than a concept with a clear physical mechanism. This theory seeks to bridge that gap by introducing a triadic system model as a new framework for understanding non-locality. We argue that traditional methods fail to account for non-local phenomena because they rely on reductionism, breaking systems down into smaller independent parts. Instead, our model proposes that non-locality can be understood through the holistic, interconnected dynamics of triadic systems, where groups of three interrelated objects act as a single, balanced unit. By focusing on the correlations between objects in a system, rather than isolating each object individually, we provide a more intuitive and logical explanation for how non-local interactions occur. The core issue with existing interpretations is that they lack a clear causal mechanism to explain the instantaneous non-local effects seen in entangled systems. While the wave function provides a useful tool for calculation, it does not address how non-local connections between particles arise in the first place. This leaves a gap in our understanding, especially when trying to apply the principles of quantum mechanics to larger systems or when attempting to unify quantum theory with general relativity, where locality is a key feature. Moreover, the reductionist approach inherent in wave function analysis doesn't capture the holistic nature of non-locality. Entangled systems behave as indivisible wholes, and yet we continue to model them by artificially separating them into parts for mathematical convenience. This separation obscures the underlying reality of their connectedness, leading to an incomplete picture of how non-local interactions work. Our triadic theory introduces a new way to think about these systems. Instead of breaking them down, we treat them as interconnected wholes from the outset. By examining the relationships and correlations between groups of objects, triads, we can better understand how non-local interactions emerge naturally from the structure of the system. This provides not only a mathematical tool, but also a conceptual framework for understanding how physical systems behave in both local and non-local contexts. In this examination, we will show how triads of objects, whether particles, fields, or even larger systems, can form logical structures that allow for non-local effects without violating the principles of causality or the speed of light. By shifting our focus from individual objects to the dynamic relationships between them, we can offer a logical mechanism that explains non-locality as a natural consequence of interconnected systems, rather than as a mysterious, spooky action. We will also explore how this model can help resolve some of the outstanding questions in quantum mechanics, particularly those related to entanglement and field interactions. By moving away from reductionism and focusing on holistic system dynamics, we aim to offer a fresh perspective that not only explains non-local phenomena, but also connects them to the larger framework of physics, from classical mechanics to quantum theory. Our understanding of physical systems has long been rooted in local interactions, cause and effect chains that operate over observable distances. However, the discovery of quantum entanglement and its non-local nature has forced us to reconsider this framework. While wave functions offer a mathematical description of these interactions, they do little to explain the underlying mechanism. To address this gap, we introduce a triadic system model, which provides a more intuitive and logical explanation for non-locality by focusing on the relationships between objects in an interconnected whole. The following sections will outline how triadic relationships can model both local and non-local interactions, providing a more complete understanding of how systems of objects influence each other. Logical triads as models of physical systems. The fundamental premise of our theory is that the physical world can be better understood through triads, systems of three interdependent objects. In logic, a triad consists of three elements where the state of each one depends on the states of the other two. When applied to physical systems, this concept reflects how objects or particles interact not as isolated units, but as mutually influencing components of a single system. In traditional physics, objects are often modeled as if they act independently, influenced only by forces applied to them directly. For example, Newtonian mechanics breaks down interactions into localized forces where one object exerts a force on another, and the result is a predictable sequential effect. While this works well for describing local phenomena like motion or collision, it does not capture the complexity of entangled systems in quantum mechanics. By contrast, a triadic model inherently considers the whole system. Instead of analyzing each particle or object in isolation, the triadic system looks at how all three components interact simultaneously, creating a balanced, interconnected unit. This approach mirrors what we observe in systems governed by fields of force, such as electromagnetic or gravitational fields, where the interactions between objects are not isolated, but spread across the system as a whole. Embracing holistic systems. One of the key shortcomings of traditional interpretations of quantum mechanics is their reliance on reductionism. In this view, the behavior of complex systems is explained by breaking them down into smaller parts and analyzing each component independently. Wave functions, which describe the probability distribution of a particle's state, are a classic example of this reductionist approach. When two particles become entangled, their wave functions are merged into a single entity, providing a mathematical description of their interconnected states. While wave functions have proven successful in predicting outcomes, they fail to provide an intuitive understanding of how and why these particles remain connected. They offer no causal mechanism to explain why a change in one particle instantaneously affects the other. The reliance on probability clouds and abstract mathematics leaves us with a descriptive tool rather than an explanatory model. The triadic system model moves away from this reductionist framework by treating entangled particles or any group of interacting objects as part of a single holistic unit. In this model, the the focus is not on the individual wave functions of the particles, but on the direct correlations between the objects themselves. Each object in the triad influences and is influenced by the other two, creating a network of interdependencies that governs the behavior of the whole system. This allows us to describe non-local interactions not as anomalies or abstract probabilities, but as natural outcomes of the system's structure. Non-locality and triadic connections. At the heart of our model is the idea that non-locality arises from the inherent interconnectedness of objects in a system. Traditional physics suggests that objects influence each other through local interactions, where effects propagate over time and space. However, non-locality in quantum mechanics challenges this notion, demonstrating that instantaneous connections can exist between objects even over vast distances. In the triadic model, non-locality is explained as a natural consequence of the system's structure. The triadic relationships between objects create a network of influence that transcends physical distance. When two particles are entangled, they become part of a balanced triad of interconnected states. Any change in one particle affects the entire triadic system, and since the system operates as a unified whole, this influence is felt instantly across all parts of the system. This framework provides a logical mechanism for non-locality. It is the result of the simultaneous interdependencies within the triad, rather than a violation of the principles of causality or the speed of light. This explanation helps resolve one of the key paradoxes of non-locality. How can two particles be instantly connected across space without any signal passing between them? In the triadic model, no signal is necessary because the particles are not truly separate. They are part of a single entangled system where changes in one element naturally propagate through the whole instantaneously. This approach shifts the focus from particles as individual entities to the relationships between objects, providing a more intuitive understanding of non-locality. The observable world local fields. In classical physics, our understanding of forces and motion is largely built on the concept of local interactions. Whether we are talking about the force of gravity, electromagnetic fields, or the motion of objects under applied forces, these interactions are described in terms of cause and effect, where forces act locally and propagate through space over time. Newton's laws of motion, for instance, explain how a force acting on an object causes it to accelerate according to the equation force equals mass times acceleration. This local sequential interaction is intuitive because it reflects our everyday experiences. When we push an object, we see it move. When we drop an object, it falls due to gravity. In this framework, forces act over observable distances and interactions follow a clear step-by-step process. The first three triads in our model, coexistence, equilibrium, and reinforcement, capture these local interactions. They describe systems where interactions are easy to observe and measure, and where changes propagate in a linear, sequential fashion. These triads represent the classical world of physics where cause and effect are clearly visible and interactions can be easily predicted. However, this local view of interactions is limited when it comes to understanding non-local phenomena. In the quantum world, interactions are often simultaneous and non-linear, with effects propagating across entire systems without following a clear step-by-step sequence. Non-locality as field vibrations. One way to understand non-locality in the context of the triadic model is to think of it as vibrations in a field. In a field, objects are not isolated but are connected through waves or perturbations that spread across the system. When one part of the field is disturbed, the entire field is affected. This concept applies not only to classical fields like electromagnetic or gravitational fields, but also to quantum fields, where entangled particles are part of a connected network. In this framework, non-locality is not a violation of causality, but a natural consequence of how fields operate. When one particle in an entangled pair is measured, the entire field is influenced, meaning the second particle responds instantaneously. This is akin to plucking a string on a musical instrument. When one part of the string vibrates, the entire string moves as a whole. In the triadic model, particles and objects are connected in a similar way, through the vibrations of their interconnected field. This model allows us to visualize non-locality not as an isolated event, but as part of a larger field-level interaction. It explains why changes in one part of the system affect the whole, and why non-local effects happen simultaneously across vast distances. Higher-level triads and simultaneous interaction. As we move beyond local interactions and begin to explore the higher triads in our model, the importance of simultaneous interaction becomes clear. In higher-level triads, such as inclusion, where multiple objects interact simultaneously, interactions occur across the entire system at once, rather than in a sequential cause and effect manner. These triads represent systems where non-local effects dominate and where the whole system behaves as a unified entity. Fields govern whole system behavior. At this level of analysis, it becomes apparent that fields, whether classical or quantum, govern whole system behavior. Any change in one part of the field influences the entire system. This is true in both classical physics, where gravitational fields or electromagnetic fields spread their influence across space, and in quantum physics, where entangled systems operate as one whole. The triadic model offers a framework for understanding these simultaneous non-local effects. Instead of focusing on the local, individual interactions between objects, we see how entire systems respond as unified wholes. This holistic perspective provides a logical explanation for phenomena like entanglement and non-locality, bridging the gap between classical physics and the quantum world. Looking ahead, the triadic system model of non-locality offers a new framework that not only deepens our understanding of quantum entanglement and non-local interactions, but also opens up possibilities for broader applications across various fields of science and technology. By shifting from a reductionist view to a more holistic approach, the model provides a conceptual and practical basis for exploring new avenues in both theoretical physics and applied research. One of the most significant implications of the triadic theory is its potential to unify classical and quantum physics under a common framework. Classical physics is built on the premise of locality, where interactions occur through direct contact or forces acting over observable distances. Quantum physics, on the other hand, reveals the existence of non-local phenomena, where objects influence one another instantaneously across vast distances. The triadic model bridges this gap by showing that both local and non-local interactions can be understood through the same structural principles. In local systems, the first triads of coexistence, equilibrium, and reinforcement describe how objects interact through sequential, observable events. At higher levels of complexity, non-local triads such as inclusion and simultaneous interaction explain how whole system behaviors arise in both classical fields and quantum systems. This unifying approach offers a pathway to resolving some of the outstanding problems in modern physics, such as the difficulty of reconciling quantum mechanics with general relativity. If both classical fields and quantum fields can be understood through the dynamics of triads, there may be a deeper underlying structure that connects them, allowing for a more seamless integration of these two pillars of physics. The triadic model's emphasis on holistic system behavior could have profound implications for how we think about information transmission and communication. Non-local interactions, such as those seen in quantum entanglement, suggest that information can be shared across distances instantaneously, bypassing the constraints of time and space typically associated with communication. By understanding non-locality as a field-level interaction rather than an isolated anomaly, we can begin to explore new ways of transmitting and processing information. This could lead to advancements in quantum computing and quantum cryptography, where entangled particles can be used to perform calculations and transmit data in ways that are fundamentally faster and more secure than classical systems allow. The triadic model provides a theoretical basis for expanding these technologies, helping to unlock the potential of non-local communication in practical applications. Another key implication of the triadic system model is its potential impact on our understanding of fields and energy dynamics. In both classical and quantum physics, fields govern the interactions between particles and objects, but the exact nature of how energy and information propagate within these fields is still not fully understood. The triadic framework suggests that fields are not just passive mediums for transmitting forces, but are active, interconnected systems where any change in one part affects the entire system. This has potential implications for fields such as electromagnetic theory, gravitational theory, and even cosmology, where large-scale field interactions govern the behavior of galaxies, stars, and other celestial objects. While non-locality is most commonly associated with quantum mechanics, the triadic system model suggests that non-local effects could be present in a much broader range of systems, including biological and complex adaptive systems. In biological systems, for example, cells and organisms often interact in ways that seem to transcend traditional cause and effect models, with changes in one part of a system having immediate effects on distant parts. The triadic model could provide a new way to understand non-local interactions in biology, such as the way neurons in the brain communicate through complex networks, or how ecosystems respond to changes in the environment. By treating biological systems as interconnected triads where each component influences the others simultaneously, we may be able to develop more effective models for understanding neural networks, genetic interactions, and ecological dynamics. This broader application of non-locality could also have profound implications for the study of consciousness and cognitive science. If the brain operates as a triadic system where different regions are interconnected in non-local ways, it could explain some of the more puzzling aspects of human cognition, such as the synchronous firing of neurons across distant parts of the brain during certain mental states. The triadic model not only has implications for scientific research, but also raises important philosophical questions about the nature of reality and interconnectedness. Traditional models of physics are built on the idea of isolated objects interacting through forces that obey predictable laws. However, the triadic system suggests that the world is far more interconnected and holistic than we previously thought. This challenges the traditional atomistic view of reality, where objects are considered separate entities with distinct boundaries. Instead, the triadic model implies that objects and systems are defined by their relationships to one another, with interactions occurring at a fundamental level that transcends distance and time. This view aligns with many non-Western philosophical traditions, such as Buddhism and Taoism, which emphasize the interconnectedness of all things. Moreover, this model invites us to rethink the concept of causality itself. If non-locality is a natural feature of the universe where events can influence one another instantaneously, then our traditional understanding of cause and effect may need to be revised. This could lead to new ways of thinking about time, space, and the nature of existence, with potential implications for fields as diverse as metaphysics and theology. The triadic system model offers a powerful new framework for understanding non-locality, entanglement, and whole system interactions across both classical and quantum realms. By moving away from reductionist models and embracing a holistic approach, this theory not only resolves long-standing paradoxes in quantum mechanics, but also opens up exciting new avenues for research across physics, biology, information theory, and even philosophy. The implications of this model are profound, ranging from practical applications in quantum computing and cryptography to deeper philosophical questions about the interconnectedness of reality. As we look ahead, the triadic system offers a new horizon for understanding the physical world, one that emphasizes the importance of relationships and interdependencies over isolated objects and linear causality. In doing so, it has the potential to reshape our understanding of both the microscopic and macroscopic workings of the universe.